Hello and welcome to this tutorial. Today I'm super excited because we are going to implement DBSCAN algorithm and also will bring some good comparison between Kmeans and DBSCAN into the picture. So if you recall your memory, then you might know that the Kmeans implementation.py is the script from the previous implementation tutorial where we implemented Kmeans and we generated 4 clusters and we visualize it, right? So however, today we will reuse this script because in order to make comparison between Kmeans and DBSCAN, we need this script, number one, and number two, we need some section of the code from here to be reused in DBSCAN as well. Okay, so let's get started. At first, if we focus in this particular part of the code, we use this section of the code to find out the optimal number of clusters. So let's check it. And now, before that, we have something very important to perform today. So let's get back to the dataset so that I can make myself clear what changes we are trying to bring in the x numpy array. Okay, so this is our dataset and we are dealing with balance and estimated salary. If you see the values, it's 0 here, 83,000 here, some 1,59,660 here, and so on and so forth. So if you try to analyze the structure, they are not very generalized. Okay, somewhere it's really low, somewhere it's really high, somewhere it's in between. Like there is no general pattern of the values. So such continuous values are not very healthy to feed on to the clustering algorithms. So we have to generalize this attribute, the value of this attribute, and the values of this attribute as well. Okay, so the technique is called normalization. I'm not going to describe what normalization is. If you just Google it, you will get very simple and understandable intuition about normalization. But you still can look here that how the values will look like once you perform normalization over an attribute. We need to import some library from sklearn.preprocessing. Import minMaxScaler is the class under this package that is used for normalization. So we take an object train underscore norm, or no, doesn't make sense, norm data. Initialization, and then we normalize our data using this object norm fit transform x. So let's compile this section of the code. Alright, so here we can see that the values are in the new format, and if you inspect all the values here, you'll find out these values are varying within 0 to 1. Yeah, and the ratio is distributed just maintaining these ratios. Okay, so however, the weights are not changed, but they are now in a journal format. Alright, so this is what we exactly wanted. We wanted to generalize, or we wanted to put our continuous values within some range, and the range here is 0 to 1. Okay, and we performed it for both of the attributes. Yeah, so this is how I've done. Now let's talk about this section of the code. This one we used just to find out the optimal number of clusters, and we talked in larger extent in the previous tutorial what this section of the code is doing. So Let's compile it. And yes, here it is. So there is a critical change in this point of the graph. So we take 4 as the optimal number of clusters for this problem. Yeah, but however, we don't need this code anymore. So for this tutorial, I'm deleting this section. Okay, you can still find this section in the previous tutorial if you follow that. Yeah. Now we perform Kmeans clustering with number of clusters with 4, and let's compile this part as well. Yes, this is the cluster, these 4 clusters we had, though we are initially visualizing, but this tutorial is not much dedicated to the visualization, but we will talk about the quality of the generated clusters. And the measure that we're gonna use to determine the quality of the generated cluster is homogeneity, or in some research paper you'll find this term as accuracy of the cluster. And for that, what we have to do, let's go back to our dataset and let's talk about this target class. So in supervised learning, you will come across this term label or target class or target label so many times, but in clustering it's not a word that is used very frequently. But for determining the homogeneity of the cluster, you have to consider this part. You have to consider your target class. So exited, this is the target label or the target class for our dataset, containing values like 0 or 1. There could be 0, 1, 2, 3. Yeah, but the values have to be discrete in target class. They can't be continuous for target class. Okay, so now if you talk about this variable y, what this variable is containing, let's check it out. Right, it's containing 0, 1, 2, 3, 0, 1, 2, 3. These are the labels of the cluster, of the generated cluster. Like the cluster, the one cluster is labeled as 0, the other is as 1, the another is as 2, and the left one is as 3. Okay, so these are just labeled just to distinguish among clusters, right? So now we want to find out the cluster labeled as 0, what data points, or more specifically what target label it is containing. Okay, so for that we have to find out the indexes of all the data points that are associated with cluster labeled as 0, right? So if we find the indexes for cluster labeled as 0, using those indexes we can find out the target label, right? Okay, so now we'll do that. Okay, let's make some space for it, and before that we have to find out how many labels we have for generated clusters. It is very much specified here as 4, but we want to make it dynamic. We want our program to find it out how many clusters were generated, and through that number we'll run a loop and we will iteratively find the target labels associated with each data point of corresponding clusters. I hope I cleared myself out. Yes, so for index out, first let's take the cluster indexes or cluster labels generated by np dot unique. Yes, so the y containing all the labels of all the clusters. So we want to find the unique value. Let's say if 4 clusters were generated with label 0, 1, 2, 3, then this is the output that this unique will find out for me. All the unique values of y will be outcome of this function. Okay, so as parameter I'll put y in here. Let's try to print this out. See, 0, 1, 2, 3, because we have total 4 clusters. Now upon this we'll run a loop. Okay, so as it is a list, we can write it like for index in cluster labels, right? But we still need the list of all the target class in our program, right? All the target classes along with their index, right? So let's do it here. And let's label it as truth, because in terms of clustering we call target label as ground truth. So that's why I've set the name as y_truth. And if I'm not wrong, the index of the target class is 13 here. So let's put 13 over here. 13, and should be done. Yeah, let's compile this section of the code, and y_truth, and yes, all the target labels are here. So now in this loop we'll do something like this. We'll take an object, we'll take a variable cluster where we will store all the target labels assigned in a particular cluster, because through this loop we will iterate over all the clusters, and for each cluster we'll find the corresponding target classes, right? So for that we already have y_truth, and when y is equal to a particular index, that is this, right? And let's say the index is -1 in the first iteration. So for all the -1 in, sorry, let's say it's 0. So for all the 0 values here, we'll get corresponding index, and using that corresponding index we will get the corresponding target class, and that we are storing in a cluster variable, right? Now what to do with this cluster variable? Okay, so how do we calculate homogeneity of a cluster, right? How do we calculate homogeneity of a cluster? That is, let's say we have 0 and 1 as our target class. So if in a particular cluster, let's assume there are 30 data points and 18 out of them are 0 and 12 out of them are 1. So there are the zeros, the target class zeros, or the data points associated with target class zeros are bigger in number in this case, right? So the cluster is representing target class 0, and the other 12 values representing target class 1 are actually impurity of that cluster. So how do we calculate this homogeneity? Value of total zeros in that particular cluster divided by, okay, let me write this for you. Homogeneity equals to the most frequent target label divided by total data points Yes, so this is the formula of the homogeneity. So it will give you an outcome, or it will give you an outcome as how much pure your cluster is in terms of the target label which is being represented by your cluster. That means if your cluster is representing target label 0, so upon that, how much pure it is, how much pure your cluster is, right? Okay, so for calculating this, we will define a function somewhere here. Okay, somewhere here, which is def yes, and we'll take a parameter cluster which will pass from here, which we will pass this variable. Okay, so first of all, we'll try to find which target label is most frequent in this particular cluster. So for that, let's take a variable count, np dot bin count and cluster. Yes, and count equal to np dot argmax So rather than which target class is being represented by a particular cluster, we need to know that what is the count of that particular target class. So these two lines are giving me that particular information, right? That let's say if zero like data points containing target label 0 has like, if data points containing target class 0 are 18 in number and the other data points are 12 in number, this part of the code will return 18, and the count variable is storing that value for us. So now what we have to do, count divided by the total members of that cluster, right? So homogeneity is equal to np dot count non-zero Okay, I actually said something in a wrong format. In here, you will actually find the target label which is most frequent in a particular cluster, okay, and np.count non-zero, it's actually counting a particular number of data points that's containing this count variable's value as a target class. That means this is the first step where we find out which target class is most frequent and in here number of most frequent data point, number of most frequent target class instances divided by total instances in a cluster. Yes, that's how it's working here, and we are just returning the homogeneity. All right, so this should be simple now, that we'll be storing all the homogeneities, because we'll get 4 homogeneities here. So let's define a list here and an integer variable. All right, so homogeneities dot insert, and in here the index, and the method we have to call it from here. Oops, something went wrong here. Yes, we have to take it from here, in here, and should be okay. Now we will store 4 different homogeneities for 4 different clusters. So when we have the final list, we will just min it, right? So print, and list values can be averaged using np function, np.mean, I mean numpy function, and something went wrong syntax wise here. Okay, now should be okay. And I think we don't need the visualization part anymore, so we can just delete this, because we are more interested in calculating homogeneity in this part. All right, so let's run this, and here is your final homogeneity for the average homogeneity of all the 4 clusters, and that is 0.807760 and ... So now we'll try to generate some DBSCAN clustering, and we'll try to prove that we'll try to show that the homogeneities, the average homogeneities of all the cluster is bigger or better than this. Okay, so let's create a file now, DBSCAN implementation.py. So the new script is ready. Let's reuse some code. We all need yeah. So here, instead of Kmeans, we'll use DBSCAN. Yes, that is already there. And for DBSCAN class under this package, you can go through the scikit-learn official documentation. It's really informative and very helpful. So if you want, you can go through this documentation, very well and organizedly written. Okay, so also for evolution, we'll take this method as well. Yes, and then this part, yes, and now we have to write a class which can actually perform DBSCAN over our dataset. So DBSCAN equal to DBSCAN, and if you inspect the parameter, we have EPS mean underscore samples. You know what is EPS? The EPS value of neighborhood. Yeah, So what is EPS? I'm just trying to recalling from previous DBSCAN intuition tutorial. So EPS is the value in this algorithm. It's the value that between two data points, the distance should be less than or equal to this value in order to be neighbors of each other. That means if two data points are trying to share neighborhood between each other, their distance should not exceed 0.5, right? So this is the definition of EPS. If two data points are trying to share neighborhood and somehow their distance value is exceeding this limit, they can't be neighbors. So in order to be neighbors, the value has to be within this limit. The distance value has to be within this limit. So the mean samples 5. So here it is written as mean samples. This is nothing but minPts from the previous tutorial, and it was about if a particular data point in a cluster wants to be a core point, you know what core point is, then it has to share neighborhood with 5 other data points. No, actually 4 other data points, because it is sharing neighborhood with itself as well, right? So min sample, this is the minimum number. If the limit is exceeding this value, then if the number of neighbors for a particular data point is exceeding this value, that's not a problem. Still, that will be a core point. But this is the minimum. This is the minimum number of data points should be in a neighborhood of a particular data point in order to be a core point. And the metric is the distance measure, which is by default Euclidean, and other parameters, they are not very useful for now. We don't have to specify them. We are just interested in these 2 parameters, and we'll grab that from there to here. Yes. So now, one very important question: can we just randomly put 0.5 as a value of EPS? Absolutely not. Absolutely not, because it will vary from dataset to dataset. It entirely depends on the property of the dataset. So I went through several papers to find out how can we optimally determine the value of EPS for a given dataset. Yes, so I found this paper as most convenient one. I'll provide the link of this paper so you can go through the paper for some additional information over the fact. So this is the procedure we are going to follow for this particular problem, where what we do here, we take one single point on our data set, and from that point we measure distance from all the other points, and then we move to the second point and we do the same for the second data, for the third data, fourth data, and we take all the distances, right? So for one particular data point, let's consider one particular data point in your data set, and from that point we have a list of distances for all the other data points. So the algorithm is suggesting, the paper is suggesting that we will take 3 nearest neighbor of that particular data point. All right, and we do it for each of the data points, and we keep constructing the k distance with the number of instances, with the index of the object. In the x-axis we have object, and in the y-axis we have k distance. And wherever in the curve we find a critical change, that will be the best EPS value for that particular data set. So we are going to implement this concept in our implementation. Let's take a new script that will be nearest neighbor.py. Yeah, So we are exactly going to implement what we saw on the paper, but there will be a little change. They have taken 3 nearest neighbor, and maybe later they averaged the k distances for 3 neighbors for each data point, but I'll take just 1 nearest neighbor, okay, and that won't make much difference on the result. That's what I believe. Okay, so here actually we'll take all this and paste it up. We don't need Kmeans, but there's a library for nearest neighbor calculation in scikit-learn, and we also have sample code here, so we'll take this package. Yes, and I think all the imports are okay. Yep. And yes, this part, because however, oops, I have to copy this. So the white truth part, I mean the target label part, is not required for this script. We just need the attributes we are dealing with, right? So we'll take this part where we are applying the nearest neighbors, and yes, in here we are supposed to put 1, right? But we won't do that, because why we are not doing it? Because the nearest neighbor of a data point, is the data itself, right? So that's not what we are looking for. We are looking for what other data point is closest to that particular data point, right? So that's why we are taking 2 neighbors. The first one, however, is always going to be the distance from itself, and the second one will indicate for other data points, right? So that's why we are taking n neighbors. So if we had to find 3 nearest neighbors, we would put 4, always 1 greater than the k value for this particular, for this particular class. All right, now we want all the distances and indices nbrs dot or something k neighbors, yes, and x is there. So what this portion of the code is doing, it's returning all the distances and all the indices here, though we don't need indices for this problem, but still, let's see what are the outcomes. Distances and indices. Yes, we have all the indexes of a particular data point, the nearest neighbors index for one particular data point, right? And now if we see the distances, oops, why it's showing 3? Because, oh sorry, you have to put 2 here. Yes, now we have 2 distances, and the first row, the first column, if you see, all the values are 0, because I said, just the way I said, that the first column will always calculate distance from itself, and this is the second part where it's like accept itself which data point is the closest data point of a particular data point, right? So we have all the values here. Now we have to construct these values in a graph, and we have to find out where the critical change takes place. So first we have to sort it, because the algorithm suggests So if you check it, this is the algorithm we are following, and sort distances ascending and plot to find each value. So we have to sort it ascendingly, right? So distances np dot sort distances, right? Now we can actually plot, and before plotting, as we are not interested in this column, we can just exclude it from the distance matrix, right? Distances is equal to distances, we take all the rows but just the column indexed as 1. The first one is 0, so the second one is 1, right? Now let's check it out if it's working properly. Distances, and yes, right. But is it sorted properly? Oops, I have to specify the axis. Yes, and how axis 0 is, you know, indicating the second column in our distance matrix, because the first column, as far I know, is always indicated as -1 here, and the second one is 0, the third one is 1, the fourth one is 2, right? So yeah, let's check it out. Now all these zeros are in their first in the row, second, third, fourth, fifth, sixth. Yeah, all the values are well sorted. Now we want to plot them in the graph. So plt dot plot, plt was defined here. No, sorry. Plot the distances. So let's check the graph. So it's turned somewhere between 0.01 to 0.02. There's a critical change, right? So okay, let's take 0.2 as our EPS value. So the purpose of this script just to generate this graph and find out where the critical change is taking place in the graph. Yeah, so for further details and further analysis, you can go through this paper. Yeah, so getting back to the script, and 0.02. As the EPS value is really low, the standard here is to keep mean underscore samples parameters value also low. So we'll put something like 10 here, should be okay. Yes, so now we want to predict dot fit predict and x. Yes, so let's check, and the rest of the part should be the same. Yes, should be the same. Not this one. So first let's find out up to this part of the code, just to check how many clusters our DBSCAN algorithm is generating. Reload, and cluster labels. Oh, total 12 clusters. So, and that's not specified, right? Like Kmeans, we can't specify number of clusters. So our DBSCAN algorithm with this particular parameter values, it has found 12 clusters in our churn modeling dataset. Okay, so now for these 12 clusters, from like we want to exclude this -1, right? Because they are noise. They are noise in our clustering environment. So we want to exclude -1. And let's do it here. Because -1 is the label for noise points, and you know what noise points are, right? So if index is equal to -1, then probably do nothing else. You perform these things, but for -1 you perform nothing, right? And oh, one thing I did mistake in here, that is I did not increase the value of I. Let's check it again. 0.807760. okay. However, it was dynamically calculating. This is the power of Python. Sometimes it updates the values by itself, so the value is not changed. However, but still we want to increase the value of the index. Yeah, and also in here. Yes. So let's run this up, and whoa, 86 is the homogeneity here, and for Kmeans it was 80%, and here it is 86%. So that's what I said, that DBSCAN promises much better clustering, much better clusters than Kmeans, and we have already proved that using our churn modeling dataset. So you can also make your own experiment using other datasets as well, right? So that was all for today, and I'll see you in the next time. Until then, enjoy data science.